have missed the first 10 minutes, but. So, should we do another one or two of these?
Can we do one where it gives us the statement we have to like find the graph? You know what I'm saying? Like when it's in the parentheses and has the -1, and that means you have to go to the right and all that.
Okay. So, I guess I'll just erase this. So, we'll go the other way. So we've got, say, the absolute value of x minus 1. In fact, I'll put plus 2. We'll do a couple things. So here we need to know what the basic function looks like. So the basic graph here is the absolute value of x. Next we'd have to figure out, okay, what is the absolute value of x minus 1? Well, in the absolute value of x, the key point was where we had 0 inside the absolute value. What gives us 0 inside the absolute value here? X equals 1. So the key point moves actually to the right 1 unit with the x minus 1. And then what happens when we add 2 to that? That moves everything up 2 units. So here's our final graph for the entire function. The absolute value of x minus 1 plus 2. And here, in fact, we kind of did this in 3 steps. Or maybe a couple steps. We looked at the absolute value function. What does x minus 1 do? What does the plus 2 do? So sometimes when we see complicated functions, we may be asked, well, say, how is this a composition of simpler functions? We'll also do composition. Given 2 functions, what's the composition? But decomposing, I think, is a little more challenging for students. Here's the net result. How can we look at that in simpler pieces? So we start from the inside and we work our way out. So here on the inside, the first thing I do is x minus 1. And so h is our inside function. And we can either say it's x minus 1, and then what do we do with that? We take the absolute value of it and add 2. Or we could say, well, the first thing I do is take the absolute value of x minus 1. And then what do I do to that? I add 2 to that result. So in the idea of decomposing, there are a couple different orders we could do this in. It's going to be the same result when we do the composition. As we work through this now that we've done it, g of h of x, h is done first, x minus 1, g of that is the input for the g function, so it's the absolute value of the input plus 2. So it's the same function we had here, it's just we broke it down, in this case, into 2 smaller pieces. And there's not just one way to break it in 2 smaller pieces. In fact, there's a sense we almost broke it down into 3 smaller pieces as we were graphing it. The absolute value, what does the x minus 1 do, what does the plus 2 do? So in a sense, when we're shifting our graphs around, either starting from the rule and what's the graph going to look like, or what's the graph, how did we shift it, we're again kind of doing 2 different orders of things. From the information we're given, what's the graph look like, or here's the graph, what's the information that goes along with it. So, is that the type of thing you were wanting to to see?
Yeah, thank
I mean, we'll not see a lot. Well, here's one a bit more difficult. Let's look at this one, just to do one more. So we've got the two graphs. We've got the original graph. What's our original function here? The cube, x cubed, not the cube root, but f of x equals x cubed. And then we've got, I'll go ahead and do this one in red, graph that looks something like that. So we've got to kind of think, okay, how did we get from the blue graph to the red graph? The basic function is x cubed. Have we done any kind of horizontal shift? Yeah, I think we moved this 1 unit to the right. Because the key point here ends up moving to the key point there. I'm not sure my graph is quite as pronounced there for the key point. I think here it's a little clearer. And we also moved up 1 unit. To the right 1 unit's a bit more of a challenge. But again, if we just think right 1 unit first, I know it's x, it's either plus 1 or minus 1 cubed. Well, for an output of 0, it's got to be x minus 1. So that when x is 1, I am cubing 0. That's where it would give me the point. And then I'm going to move that up 1 unit. But in this case, there's one other thing that's happened. Yeah, we flipped it, well, either vertically or horizontally. And that's a challenge with the power functions. We're going to look at is flipping it vertically. What flips vertically? What makes a vertical flip? Well, what makes a vertical flip is the negative of the original function. And so in terms of what we've got here, A is what's multiplied outside. And so here we multiply by -1. We haven't really done anything with B, I don't think, here. Actually, I think we may have, but, well, not. C, we're adding a -1. And D, we're adding a +1 outside. And let's see how we did. Well, we did pretty well. We actually, when we flipped it, we did a little bit of stretching too. And that's a hard thing to pick up on, that we actually stretched a little bit. So actually we multiply not by -1, but probably -2. And that is kind of the hardest thing to see. Not only did we flip it, we stretched it.
So on the test, if we miss that cube, would we mark down by very much?
That's probably where the least deduction would come. Although, I mean, a problem like this, it's probably, you know, a series of questions. The whole series is maybe 10 points, so 2 or 3 points for each part. And typically, if I can figure out where the mistake was, it's 1 point for each mistake. So if you got, just had minus instead of the -2, that'd be no more than a point. And depending on the other parts of it, actually, I guess for this, there's probably 4 or 5 things you've got to kind of get. Identify that it's the cube function, that's a point. that you moved horizontally, how much and what does that do? Move vertically, and what's happened with the flip and or stretch. So there's probably 4 or 5 points in that problem. But definitely the stretching, especially following the flipping, this one, that was a hard one to really kind of see that not only did we flip it vertically, we stretched it a little. I mean, once we graphed it, we could see, oh, it's not quite right. There's something else going on. So once we did the wrong thing, hopefully we realized, oh, it did stretch a little bit. But without that, it's quite a challenge to see that we really did stretch. Normally going over 1, we'd go up 1. Well, we went up 2, so we did stretch a little bit, but that is a harder, for some functions, that's a harder thing to see. Some other functions, I should have gone with the parabola there. That one I think is a little easier to see that we've done some stretching, because the parabola is going up more rapidly in the red one than it was in the blue one. So that one, there is a little stretching. We could look more closely, but probably by a factor of 2. We moved it down 1 unit. And to the left 3 units. And so to the left 3 units, it's x plus 3 that's inside the parenthesis rather than x minus 3, because the vertex is now over at -3 rather than at 0. So we know this is the basic square function here. We can identify it's the basic square function. The vertex is over here at -3, -1. So we move it left 3 units, down 1 unit. Well, to get the vertex over here, it's x plus 3 squared. That's where we're going to be squaring 0. And then we move it down 1. And then in this case, we stretched a little bit more, because this one's narrower than what we had before. So I think we probably got that here, and we do. But here, even if we decided stretch some, it is a bit more of a challenge to figure out, did we stretch by a factor of 2 or a factor of 3? Or some other factor. I mean, the common factors here are 2 or 3. The negative one, which just flips it, is fairly easy to see. I mean, for some functions, it's easier to see a stretch. I mean, here, hopefully you spot there's been a vertical stretch. We have to look a little closer to figure out, well, how much of a vertical stretch. Normally, over 1, up 1, here over 1. I think we're going up 3. So we've actually stretched by a factor of 3 here. Moved it to the right 3 units and down 2 units. So we can identify what the basic graph is, what sort of transformations. So again, we could come up with, well, what is the basic equation here on this particular graph? We've decided we've done a vertical stretch. It was the absolute value. Moving over 3 units, it's an x minus 3, because that's where the absolute value will be 0 and have our corner. But we've also moved the corner down 2 units. So we get 3, x minus 3, and then minus 2. And hopefully that's our graph. For the functions we've been looking at, we're very seldom going to do any kind of horizontal flip. And for the parabola, horizontal flip doesn't look any different than the original function. Absolute value, horizontal flip doesn't look any different than the original function. The reciprocal, horizontal flip doesn't look any different than vertical flip. So there are a couple that functions where a horizontal flip could be also identified as a vertical flip. Either way is accurate and could describe what the final result is. So those were some things that were not on the review, working with that. There were things on here in terms of composing functions. We've kind of gotten into composing functions here, looking at the transformations to compose functions. Also, kind of once we've got the transformation given, kind of decomposing that to figure out what were the simpler pieces to put that complicated function together. And then we started looking more specific information on different functions. So we kind of did, I think, 2 sections on functions in general. The basic toolkit functions, transforming the toolkit functions. One, 3, then we looked specifically at linear functions. Where we can identify the slope and the y-intercept. And so we could be given the slope and the intercept and coming up with the equation, come up with the graph, given it, say, in verbal form, and told it's a linear function, and coming up with the equation. So there are a number of things we could do there with linear functions. So for example, if we go to the worksheet with this one, we try to find one that's, we'll look at this. We've got some points. What do we have here? 1, negative 2, and 2, negative 1. So the slope, change in y over change in x. We've got a slope of 1. And we should be able to look at our points and realize, is the slope going to be positive or negative? Are we rising as we go to the right or falling? So we should be able to tell positive or negative. So the slope here is 1. So our basic equation is y equals x plus b. But b is nowhere in what we're told. We can use one of the points we are told. Negative 2 equals 1 plus b, and we can solve for b here. B then is negative 3. So our equation in this case is y equals x minus 3. We can read off what the slope is. We calculated the slope. We calculated what the y-intercept is. And if we check it, the line we have should go through the points. That's what we're trying to do, is figure out what line goes through those points. We really only needed 2 of the points. Any 2 of the points would have been fine here to work with. No matter what 2 we pick, we should get exactly the same slope of 1. And no matter what point we use then to figure out the y-intercept, we should still solve. But it does require some solving. The y-intercept was not given to us. So just because it goes through 1, negative 2, doesn't mean the y-intercept is negative 2. We're going to figure out, okay, what is the y-intercept based on the fact it goes through, in this case, 1, negative 2. So we did some things with lines. Back. Up. I'm going to have to start.
How many questions are going to be
I don't remember. Um, Ten to 12, and I mean, some of them have parts. So like, here's an equation, what's the slope, what's the intercept, graph it. Do you count that as one question or three? When I say 10 to 12, I've counted it as one. But they all kind of fit together. Or, here's a graph, what's the basic toolkit function, how we transformed it. If we write down the rule based on how we've transformed it, since from the graph we could read off, say, what f of 1 is, or where is f of x equal 4. So there are ways some things could be combined. That would also be like one question, even though it's got 3 or 4 parts in it. So I think there are 10 to 12 questions like that, but a lot of them have 3 to 4 parts.
What else other than those two? Like, will be more problems that are going to be on it? Like those two will be on that, like stuff like that, then what else?
So there'll be a problem or two about simplifying exponential expressions. So we need to remember, what if we've got x to a power times x to another power? What happens with the powers? We add them. If we've got x to a power raised to another power, we multiply the powers. If we've got x to a power divided by x to a power, if we've got a product to a power, each factor is to the power. If we've got a fraction to the power, numerators to that power, denominators to that power. I think those are the key things we worked with in terms of exponentials. For quadratics, we were interested in finding we could start with the shifted form of the quadratic. So 2 times x minus a negative 3 squared plus 3. The x minus a negative 3 or x plus 3 is going to shift our vertex, instead of being at 0, 0, 3 units to the left. Plus 3 is going to move it up 3 units. And then the times 2 is going to shift it, or stretch it. So we're going to get a graph kind of looking something like that. And we could check to see, is that really the graph we get? There is the actual graph. I did such a good job we couldn't even see the blue graph. Or maybe such a bad job of writing it so many times we couldn't see the blue graph. Normally we will start with a quadratic in this form. So normally we'll start with, say, this kind of form, x squared plus 7x plus 12. We are not going to try to break that down into how we've shifted the quadratic. If we're starting in that form, we're going to be looking for where is the x-intercept. So where is the y-coordinate 0? Where is the y-intercept? And where is the vertex? So for the x-intercept, we need to know where y is 0. So we've got to solve where is this quadratic equal to 0. two different ways we could try to solve that. Anybody remember one of them? We could factor. Does this factor?
Yes. Plus 3 plus 4.
X plus 3 and x plus 4. So negative 3 and negative 4, 0. So those are 2 points the quadratic goes through. Or we could go to the quadratic formula. The y-intercept, what happens when x is 0? We plug in 0, we get y equals 12. So even here with the quadratic, we're doing some solving, whereas the quadratic equal to 0, we're doing some evaluating. What happens when we plug in x equals 0? So we're going to wade through here 0, 12. The vertex occurs when x is negative v over 2a. So in this case, negative 7 over 2 times 1, negative 7 halves, or negative 3.5 if we put it in terms of a decimal. This x-coordinate always should be evenly spaced between the two x-intercepts. There's a line of symmetry going through the vertex, so it has to be halfway between the two intercepts. But we're not done. We also need the y-coordinate of the vertex. And this is harder with the decimal. I think we get, if I go back to fractions, 49 minus 49 halves plus, I'm going to write it as 48 fourths. And that's actually 98 fourths. So I think we end up here with minus 1/4. Just a little bit below there. And we can pull out our calculator and do that to evaluate the function. And I will have some calculators I'll bring as well. We've got some graphing calculators I'll bring that we can loan out during the test. So this one asks, okay, where's, what's the x-coordinate of the vertex? So we decided here there was negative 3.5. The y-coordinate is negative 0.25. One x-intercept was at negative 3. The other one was at negative 4. This parabola actually does open up. We've decided, from what we've got, it would be opening up. So I'll check this box. And now we should show the graphs. And what it's going to show us are two graphs. The graph that does go along with that parabola and the graph that goes along with all the information we put in. If we're right, we should see this sort of candy cane striped effect because our graph is the one that's the correct graph. If we saw two different ones, say we got the vertex here wrong and said it was negative 1, not negative 0.1, negative 1. Well, we don't have the vertex in the right spot. We still have everything else kind of working correct, so it may not go. There would be a parabola that would go through this point and those two. It would have to be a lot steeper, and it wouldn't be the correct one. But if they match, then we do have the correct parabola, and then we can ask, give me another problem in terms of that. Actually, on this one, part of this question is extra credit on the exam.
We do know one of these, but just use the calculator. Show us how you do that, find all that without factoring all that.
Okay.
You did in class one time, but I forgot what you used.
Yeah, they calculate on the screen.
Yeah.
Okay. So suppose we had x squared plus 3x plus 5, or minus 5. I don't think factors. So the quadratic formula x is negative b plus or minus the square root b squared minus 4ac all over 2a. So negative 3 plus or minus 3 squared minus 4 times 1 times minus 5 over 2. Which I think gives us negative 3 plus or minus the square root of 29 over 2. I don't know what the square root of 29 is, but the calculator will tell me. So let's see, negative, turn it on, negative 3 plus the square root of 29, 2.38, divide that by 2, so 1.19. If we do the plus, if we do the minus, negative 3 minus that square root, divide that by 2, negative 4.19. So a little past 1, a little past negative 4 are our two x-intercepts. Y-intercept would be what happens when we plug in x equals 0. 0, 0, minus 5. The vertex, well, x is negative b over 2a. So in this case, negative 3 halves. And y is whatever we get when we plug that in. So negative 1.5 squared plus 3 times 1.5 minus 5. Yep, this times negative 1.5. And minus 5, negative 7.25. So down here, which is where I'd expect it to be. I mean, it's got to be between these two, and it's going to be lower than the y-intercept. And so we can graph this fairly well then, or for that matter, we could ask the graphing calculator to graph it for us. X squared plus 3x minus 5. And it graphs. It's just a little harder on the graph to see where exactly is the vertex. Even for that matter, where exactly are the intercepts. There are ways the calculator will find that for us. We can ask it, it would calculate where the minimum is. We have to give it a little bit of hints on where we're looking for it. And it'll go and work and find exactly where the minimum is. And notice it's at minus 1.5, minus 7.25. Same value we had predicted. We can also, I believe, calculate here the zeros. And again, we've got to give the graphing calculator a little help. Get on one side, on the other, give it a guess, negative 4.19.
That's not exact.
It's not exactly 0. Now, this scientific notation, e negative 12, this is 1 times e to the times 10 to the negative 12th. 0.0000000001. Essentially 0. In the way it's going about doing things, it's not finding exactly 0, but we are really close to 0 there. And then there's another 0. If we calculate the other 0, again, we've got to get a little bit of help as to where it's looking. We don't have to give it a very good guess. It'll work. This time it does tell us exactly 0, 1.19. But it is true with the zero, or for that matter, even finding the minimum, it might give us something really weird, like negative 7.24, 99999. Sometimes when it does the calculations, it does just an approximation. With the polynomials, we weren't even attempting to graph the polynomial. With polynomials, we're just trying to figure out where is the graph above and where is it below. Where's the polynomial positive and where is it negative? And in fact, with polynomials, we're starting with it already factored. We're not going to have to factor them. So say on this one, we've got what? Minus x minus 5, x minus 4, x plus 2. We want to know where this is less than 0 or equal to. Where are we going to equal 0? Where's this going to give us for 0? At 5, and at 4, and at negative 2. So those are the places we actually equal 0. And so what we're trying to figure out is, in the graph of this, not really where the peaks and valleys are. Long term, we'd like to know that. But at this point, are we above the axis or are we below? And so we just check a point, say at minus 3. At minus 3, this function is minus 3 minus 5, minus 3 minus 4, minus 3 plus 2. So I've got a minus 8, a minus 7, a minus 1, and another minus. It's positive. If you want to figure out that it's positive 56, that's fine, but it is positive here. If it's positive here, it's positive throughout. Then we need to pick another point to test. There are quite a few points in here. We could test it, say, at 0. At 0. Negative, 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 positive. 3 negatives will give us a negative. It's actually, I guess, negative 40, but the negative is what we're interested in. This one's a little harder because we've got to think carefully what's between 4 and 5. No nice numbers between 4 and 5, but we could go, say, with 4.5. We can have a negative, a positive, and a positive, well, another negative. That whole expression is going to be positive. And then past 5, say it's 6. Negative 6 minus 5, 6 minus 4, 6 plus 2. Positive, 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 but this pesky little negative out in front, the whole expression's negative. Now, we've really done a full sign analysis. We were interested in this case, where is it negative? So it's negative on this interval from minus 2 to 4, and from 5 on. And 0 is also possible, so the endpoints are actually included. And then we can click to see the answer from negative 2 to 4, and from 5 on. So the graph looks something like this. We will return to this question later on in the course. Can we figure out exactly where those peaks and valleys are? We will develop ways to do that, but for now we're just trying to figure out where are we above the axis, where are we below? Where is this expression positive? Where is it negative? And the key thing to realize, it is really not just, we can't just look at one factor at a time. It's how do all 3 factors work together to give us a positive product or a negative product. In this fact here, there are 4 factors, the negative out in front as well. So how do all the factors work together for the product? We didn't do that much with rationals, but we did some things with exponentials in terms of investments and then solving exponentials. So maybe let's see. Maybe we invest $500 at 6% compounded 4 times a year. So this particular one is set up. We can put a 1 in here to see, well, what's the equation going to look like? The 4 times a year, the end shows up in 2 places. And then it's a matter of what if we invest this for 4 years? We put in 4 for t and compute what we get. If it's compounded continuously, that's the form where the e is involved. 500 times e to the rate times t. And again, for 4 years, we just plug 4 in and figure out what we get. We didn't do anything with effective rate in here. I used effective rate in another class. But what we did do is, say, like compounded continuously. So we get 500 e to the 0.06 t. We might ask, well, when do we, I don't know, triple? When do we get to 1500? For that, we're going to have the logarithm, which is our final topic. We can divide both sides by 500. E to the 0.06 t equals 3. Convert to log form. This is one of the logs we've got. The natural log of 3 equals 0.06 t. We can solve for the time. And we can pull out our calculator then. Natural log of 3 divided by 0.06. So about 18 years. How do we know if that's right? Well, did it really solve the equation? Is it really true that 500 times e to the 0.06 times that number, 18.31, I'm hoping for 1500 or something close, because I rounded a little bit. I'm pretty close to 1500. So it is about 18 years to triple. And that's our interest in the logarithm. Can we solve an exponential using the logarithm? Because there are a lot of models that you'd see in business where something is growing either at an annual rate of 6% or sort of the instantaneous rate. And we either want to have predictions of what happens in a certain number of years or when do we reach a certain value. So again, there's the evaluate or solve. So a lot of evaluate and solve with functions. And just lots of different kinds of functions we've looked at here. I mean, we may have to go from exponential to log form as part of solving the exponential. Yeah, if it's anything other than base 10 or base e, we could just take the log of both sides. So we could have at this point taken the log of both sides. log of something raised to a power, the power comes out in front. This probably wasn't the best example, because we've got to think, how am I going to get log of e in there? But if we do this, log of 3 divided by 0.06 times the log, got to think a little bit of how I get e in there. It does give us exactly the same result, but we did have to think of a little bit, how to tell me what e is. E to the first power is e. E is actually 2.718, or we can ask our calculator what is e. Usually anything to the first power, well, 27 to the first power is 27. If the power is 1, it is just the number. So the way to figure out what e is, we ask the calculator what is e to the first power. And it will tell us this is what e is. Most of the time when we've got e to a power, we're going to use that e to the power button to just evaluate. But if we did have to know what e is, the calculator would tell us that as well. Okay. That is most of the topics. Anybody kind of, in looking at the review sheet or anything, kind of think I missed something? I did try to do, what, 4 weeks in an hour? So if you're feeling overload, this was 4 weeks of work. I tried to do it in an hour. And I think a couple may have come in late. I do have some homework to return if you think you've got some that I haven't gotten back to you yet. I didn't look at this.
Will you slow down? Dude, you gotta where you were going.
Oh, okay.
Thank you.
Let's see.